Hey guys, welcome to the next section, the learning process. We'll first understand the problems, then we'll cover dataset retrieval, pre-processing, and feature engineering. Moving ahead, we'll define train and evaluate model. Finally, we'll interpret the results. Now we move on to the first video, dataset retrieval. In this video, we're going to first understand the problem. Moving on, we'll first load datasets, then we'll input missing data, and finally, we'll be pre-processing the dataset. When solving machine learning problems, it's important to take the time to analyze both the data and the possible amount of work beforehand. This preliminary step is flexible and less formal than all the subsequent ones on this list. Once identified, the following task will generate an organized and structured set of values, which will be the input to our model. Once we've identified the data sources, the next task is to gather all the tuples or records as a homogeneous set. The big data processing field evolved over several decades under the name of data mining. One of the best outcomes of these disciplines is the specification of the extraction transform load (ETL) process. This process starts with a mix of many data sources from business systems, then moves to a system that transforms the data into a readable state, and then finishes by generating a data mart with very structured and documented data types. Let's load the datasets. We'll begin by importing and performing a simple statistical analysis of several dataset input formats. We'll work with IPython. We'll first change our path. To run IPython, we call it from the command line. Here we see IPython executing, and then the initial quick help. The most interesting part is the last line. It will allow you to import libraries and execute commands, and will show the resulting objects. Here we're using the standard Python version for the most supported Linux distribution at the time of writing, Ubuntu 16.04. First of all, let's import pandas and load a sample.csv file. We've used the iris.csv file, and it contains a very common format with one row per line and registers. It contains a very famous dataset for classification problems with the dimensions of the attributes of 150 instances of iris plants, with a numerical column indicating the class. We first import pandas in the usual way, making its method available for use with the import statement. The as modifier allows us to use a succinct name for all objects and methods in the library. Next, we use the read_CSV method, thereby allowing pandas to guess the possible item separator for the .csv file and storing in a data frame object. Next, we perform some simple exploration of the dataset. First, we enter df.columns. We're now able to see the column names of the dataset. We then enter df.head, thereby exploring the first three instances. Looking at the first registers, you can see the varying measures for the Setosa iris class. Now, let's access a sepal length subset of columns and display the first three elements. This is the command to do it. In addition to these simple exploration methods, we'll now use pandas to get all the descriptive statistic concepts we've seen in order to characterize the distribution of the sepal length column. We terminate this IPython and go back to Jupyter Notebook. So, here too we run the same commands. Let's proceed to get the descriptive statistics. We add this block of code to describe the sepal length column. Now we'll graphically evaluate the accuracy of these metrics by looking at the histogram of this distribution. This time, we'll use the built-in plot.hist method. As the metrics show, the distribution is right-skewed, because the skewness is positive, and it is of the plainly distributed type, and has a spread much greater than 1, as the kurtosis metrics indicate. Let's stop here for tabular data, and go for 2D data structures, as images are the most commonly used type of data in popular machine learning problems. We add this block of code to read images. The code is optimized to run on the Jupyter Notebook with inline graphics. We've imported scipy. This is the path where our image is present. When we run the code, we get the image. Importing a single image basically consists of importing the corresponding modules, using the imread method to read the indicated image into a matrix, and showing it using the matplotlib. The percentile starting line corresponds to a parameter modification, and indicates that the matplotlib graphics should be shown in line on the notebook, with the results. The testing variable will contain a number of height, width, and channel number array with all the red, green and blue values for each image pixel. As you can see, this is the red, green and blue values that we're talking about. Let's now separate the channels and represent them separately with red, green and blue scales to get an idea of the colour patterns in the image. For doing it, we create 3 subplots indicating the structure and position with a 3-digit code. The first indicates the row number, the second indicates the column number, and the last the plot position on that structure. The CMAP parameter indicates the colour map assigned to each graphic. As you can see, we get 3 separate colour maps. Note that red and green channels share a similar pattern, while the blue tones are predominant in this bird figure. This channel separation could be an extremely rudimentary preliminary way to detect this kind of bird in its habitat. Now we'll see different advanced ways to get the dataset, including loading and training the different batches of sample sets. So we've loaded data, extracted useful content, and finally expressed them in tabular form.